up. So, kind of a light week for us. And I just want to start off by saying I absolutely, totally enjoyed Monday. You all did phenomenal. Sorry, why is my thing? There we go. There I am. I thought you all did amazing. And yeah, so just thank you. That was a really fun night. So we're doing alcohols. We saw a preview to like a week or 2 weeks ago. I don't even know. It seems so long ago since I had to teach you guys. So alcohols just mean we're going to have an OH. And I found when I have my at nighttime, when I have the overhead light on, the colors show up different. So, you know what? I'm going to the trick, I'll just do the first one. You can do carbons or you can do zigzags. If you do zigzags, so just to be careful on this, that is not a carbon there. This would be carbon 1 and then 2. That would be 3. So we need another zag and that would be 4. So this would be 1 butanol. It doesn't matter which end you show it on. We count at the end closest. So for 2-butanol, we would show our OH. You always write the H that is on the O. So you always have to actually physically write the H. So in the zigzags, you don't have to do the other things. So I am going to pause this and I'm going to give you guys like 5 minutes to go ahead and get your brain cells moving again so try drawing, and these 3 are going to try naming. So I'm going to pause, and if you are watching this at home later, just pause me and try them. I'm going to go ahead and go ahead. Hi, Kaylee. Did you have a question?
No, I was just saying I'm ready because you said no one asked you.
Oh, okay. Thank you. This is my other class. My other class, they've actually started turning on their cameras. It's actually fun. Actually, I love when Kaylee's camera's on because I love your background tapestry there. All right. So I also wanted to comment, I have been loving the colors. So many of you are using colors on your homework, and it's really fun. It was really fun grading the celebration one because you all did really well. I start at the end, the heptanol, and you can draw the carbons. I'm going to write I'll do it both ways on this one. You can do your zigzags. And so if it ends up pointing up at number 2, we show the OH up, and then number 4 would be the isopropyl. If you show the carbons, one of the things when you show the carbons is we try to make sure our groups don't run into each other. 4, 5, 6, and 7. And then you do have to show the hydrogens. So you can show them condensed in like this, or you can just show the dashes. So again, if you write the C, just a reminder, because it's been like 2 weeks since we've done this, those dashes mean hydrogen, whereas when we're doing the zigzags, they mean something else. All right, so cyclohexanol, we don't put the number because the OH is at number 1. So wherever you put the OH, that is number 1. And then isobutyl, remember, has the elbow and then the peace sign, whereas isopropyl is just a straight peace sign or antenna. And again, you can have it counting whichever way you want, but the OH on cyclohexanol, we don't put a number. Same with cyclohexene, we don't number the ene. All right, on this one, the OH does happen to be at number 1. And we just want to go counting. If you haven't bought colored pens, these things are awesome. So there's our 7, and then we're going to have, these are our methyls. So 3,4-dimethyl. One of the unfortunate things that happens on these pages that we're doing tonight, we get a lot of OHs at number 1, and then students think the OH has to always be at number 1. And it's an unfortunate thing of my notes that just has never been fixed, but you do tell me it is at number 1. The only time we do not is on the cyclo. And great. On this one, so we got a 1, 2. This OH from the CH2, this OH is here at number 3 and at 4. So sometimes when I save to a PDF, things get shifted by a fraction of a millimeter, and that makes it funky. That's why I do the celebrations, so that I'm present and so you can come on. So if you're not quite sure, but from counting the hydrogens, 5, 6. Now, this was something that just historically students don't like, the parentheses, but you can't have a CH3 in a row. And so one of the CH3s is going to be a side group, a methyl side group at number 6, and then this will be 7. So 2 OHs, what do you think? We would say heptane. We actually write the whole word heptane, and then we say diol. It is actually really important. I think we run into it later on the notes, or we'll run into it when we do the study set. You have to have that AN there. So if you notice up here, all of them had that AN, because we can run into something where you have a double bond and an OH. And so this AN tells us it is fully saturated and that there's no double bonds. So this di goes right in front of the OL. So it's telling us there's 2 alcohols, so we need 2 numbers, which will be 3, 4, heptane diol, and then the methyl was at number 6. So it's a 6-methyl 3, 4 heptane diol. All right, this again, this is saying there's 3 CH3s around the carbon. So 1, 2, and 3. This was a question that came up in my other class, and I just wanted to point it out because you may see this happen at some point. I know it does, that sometimes when they show CH3s on the left, they write it backwards like that, H3C. It's a methyl group, it's the same, but this one actually, that's a tert butyl, and it's at number 4. And cyclohexanol. Just a reminder, this is not benzene, so we can't use OMP, we can't say para. We're going to see those on Monday when we look at the friends of alcohols. All next week, we'll look at the other groups that have oxygen in them, just 1 oxygen. All right, this term here, classifying the alcohols. Alcohols are classified as either primary, so that means primary. We just show the one with the degree sign after it. Secondary, or tertiary. And this is actually extremely important for the next page when we do chemical reactions and their properties and stuff. If the OH is at number 1, that is a primary. So 1-butanol is a primary. If it's at number 2, it is not necessarily a secondary, but both of these are secondaries. That's just a coincidence. I don't know that I have a tertiary here. This is a secondary. Oh, we drew it up there. This is a secondary. This is a secondary. These are secondaries. So I need a tertiary to show you. It has to do not with what number the OH is on. It has to do with how many carbons. So the carbon that the OH is attached to, primary means there's only 1 carbon attached to that carbon. So this carbon that the OH is attached to, there's only 1 carbon. Here on a secondary, this carbon that my OH is attached to, it is attached to 2 carbons. So a tertiary, we didn't have it up there, but we can do one. We'd have to have a carbon here with the OH, and then we'd have to have 3 carbons attached to it. That is a tertiary. Now, this one's actually a really interesting example because it has a special name, and it is called T-butanol. Hopefully you can see that. That's this example down here. So the T stands for tertiary. And that is where the term T-butyl comes from, is because of the alcohols. It's also where the term, this one up here that we called 2-butanol, that is the correct IUPAC name. And so the IUPAC numbering system, we always use numbers. But the common name for this, what a lot of people call it in lab, this one up here, the the 2-butanol is actually commonly known as sec-butanol or sec-butyl alcohol. So a lot of things had common names before they came up with the systematic way, and it is actually where the names of the butyl side groups came from. Is this is a secondary alcohol, so it's a secondary alcohol with 4 carbons. This was a tertiary alcohol with 4 carbons, so it was called T-butanol or T-butyl or tert-butyl alcohol. And so that's what primary, secondary, tertiary is. And we'll see other examples as we go through this, and we'll classify them. All right, so this is that fun game where we make a sketch, and you can do zigzags or you can draw. Sometimes with these, it's easier to draw the carbons. So we start here with 2-propanol, remembering it's going to be named wrong. And so this is where using colors can be helpful. So this is 1, 2, 3. And then at number 3, we're going to put the sec-butyl. So sec-butyl means we're attached to the second carbon of the 4. So it's named very wrong. It's numbered wrong. We do still have it at the second position, but our longest chain now has 6. So we would have 2-hexanol. And then that extra piece there is a methyl at number 4. So we'd call it 4-methyl 2-hexanol. So when I'm asking you to rename it, you can just do a sketch with the carbons. You can also do it as zigzags if you like that. I'll do this one as zigzags. So 2-butanol. So there's my OH at number 2. And then at number 3, I'm going to do a propyl. So a propyl means 1, 2, 3 in a row. So that's my propyl. So we numbered it wrong. So we have, it is 1, 2, 3, and then we go 4, 5, 6. And look at that, we have almost the same name. So this is our methyl, 3-methyl, and then 2-hexanol. And I kind of just keep going, unless somebody has a question. All right, and then on this one, and do it the way that you can count your carbons the best. So 4-pentanol, you guys have actually, most of you seem to like the zigzags. So the OH is at number 4, and then the isobutyl. So you actually want to draw it, and it's not just that we numbered in the wrong direction, because the OH we do want at number 2. It's that we numbered in the wrong direction, and we didn't find the longest chain, because when we get to number 4, we want to come up here to 5, 6, and 7. So it's a 2-heptanol. Let's do it like this. So 2-heptanol. And then I have a methyl and a methyl. So I have a 4, 6 dimethyl. Something I actually want to mention, just remembering from, I graded your celebrations like a week ago, but if you have both side groups, methyls are at the same number, like a 4, 4, you do have to repeat yourself and say 4, 4 dimethyl. So every extra side group has to have a number, even if it's repeating itself. So as we get more practice, it actually gets easier. One, because you guys have had practice, so you're pretty good at drawing them. And everything's now going to be determined by the oxygens. Like the game completely changes. And that's why I do the celebrations how they are, because in some ways it becomes easier with the oxygen there. I want to do one more thing with each of these, and that is classify them. So whenever I ask you to classify, we're just going to say primary, secondary, or tertiary. And actually, they are all secondary because the carbon that the OH is attached to has a carbon on each side. So it's a secondary. It's not just that it's at the second carbon. So again, here, this carbon is attached to 2 carbons. So it would be a secondary, and this is also a secondary. All right. So the bottom of the page, you guys do get to do another set of class presentations, which is awesome because they were fun. The next one is worth more because there is going to be a paper associated with it. I will get it posted. It's not, we're going to be doing them in the 10th week, but just something to think about. And you're going to see a section like this starting to show up on every handout. And it's part of the inspiration of the lab that I'll talk about in a little bit that you're doing for the next week. The next topic is you're going to pick a molecule, an organic molecule, and you're going to find out more information about it. There are millions of molecules. You need to find one that's going to make you go, yeah, I want to learn more about that. There is a little catch. You also have to find, and some of you actually did this and you did a really nice job. It was impressive. You have to find at least 2 studies, scientific studies that you do discuss in your paper. So this guy, I don't know how to say it, zeaxanthin. So pick a molecule you can say, and if you don't know how to say it, just fake it the whole way through and keep saying it that way because nobody's going to know. This is really almost the same thing as beta carotene, and I know it's one of the things that gives the red color, like in tomatoes are really high in it, and it's also because it gets changed, it's related to the carotenoids. It's really important for eye health and stuff, but you've probably heard of it. It's one of the vitamins. It's one of these super molecules, cholesterol, of course, and so we see the OH group. And if we wanted to classify them, this would be a secondary, and that guy would also be a secondary. Now, one of the things about these, we talked about this way back the very first lab, both of these would be hydrophobic. So anyone, why would these 2 be hydrophobic even though we have an OH on them? Because OHs, we usually think, well, water loves OHs, hydrogen bonding. That's what we get to in 2 pages. Why are these both hydrophobic though? They don't even get to be the amphiphilic things. Go ahead, Kristen.
A long chain of carbons.
Yeah, there's so many carbons there. So there is like a ratio thing, but it's really, I don't like giving that number because it's not a perfect fit, but this is pretty much almost all carbons. The water can't surround any of this. It might say, oh, hello, there's something I like, but it can't dissolve it. Even these here, these start having just too many carbons. Usually when you get past 6 or 7 carbons, it just is too many. This guy, the tert alcohol, sure. And we'll talk about solubility in a couple pages. Oh, I skipped this guy, ethylene glycol. Some of you, has anybody ever heard of ethylene glycol? You all have. I'm so proud of my Tuesday, Thursday class. I got 6 names on the board last night. I am determined, like last term, so people were in my 104. Last term, I think we had one day I got 20 names on the board. So my Tuesday, Thursday last term, I never got more than like 3 names on the board. So I was so thrilled. I got up to 6, and it's only like the 5th week. But your name on the board is a good thing. It doesn't mean like you have to wear the dunce hat, but wearing a NOF is really fun, right? I was just so excited not to have to wear black tonight because we're past the hydrocarbons and it's like Valentine's month. So I didn't really want to dress up like a bartender or something doing alcohols. And I don't know. We do, yeah. Next week we do polyphenols. This one is, so this is estradiol. Oh, sorry, back to ethylene glycol. Ethylene glycol, I don't know why it was named this way. I don't know if it was a mistake. It drives me crazy. And so I avoid this one because because the ene makes me think there's got to be a double bond, but it doesn't. It's actually ethane diol, 1,2-ethane diol. So the term glycol is also a diol. So a glycol means 2 OHs. So it's the same thing as a diol. So this is 2 carbons and an OH on each one. And right. And then it would show. They do have to number them to say the OHs are not both on number 1. That is actually what was used historically as antifreeze in our cars. So that our cars didn't freeze up when they sat out in the parking lot for a long time. Unfortunately, it has to do with the reaction we're going to do on the next page, that this got changed by our body because it's toxic. So our liver oxidizes it and changes it into an aldehyde, which turns out destroys brain cells. The bigger problem was that our antifreeze leaks, and animals, it's very sweet. Alcohols actually have a sweet taste, and animals are attracted to it and they lick it up. And small animals don't need very much for it to kill them. And it was actually, I don't know if it's banned. It's not supposed to be used anymore. It was more a problem in wilderness areas because the wildlife would come and lick it up and then die. And so the new antifreeze is I can't remember if it's glycerol, but yeah, our liver actually changes it into what causes kidney stones in us, which is just as great. This is another one that's interesting. And for those of you who are going to take Chem 106 with me, we'll talk about triglycerides. So you may have heard of triglycerides. Those are our fats. It's if you get your blood tested, they always check for cholesterol and triglycerides, but glycerol is 3 carbons and each carbon has an OH. So you don't need to remember these. I would always give the IUPAC name with it, but it's just another one. There is also, just real quick, there is propylene glycol, and I don't remember if it's ethylene glycol or propylene glycol or both. That's what's in the e-cigarettes. So I've actually had some people pick their topic as, I think it was propylene glycol. Turns out it's really bad for you. I can't believe e-cigarettes are actually even legal. And so we're just in that timeline of being the guinea pigs until enough studies have shown that this thing needs to be banned. But I think it's propylene glycol. It's 3 carbons with the OHs, and it has to do with our body changes it. Our liver changes it by oxidation. Estradiol, so estrogen. So everybody has estrogen. There's actually 3 different types of estrogen, and the ratios are just different at different times in our life. So one is estradiol, and so it has an OH here and here. But again, like Kristen said, it is actually related to cholesterol. Cholesterol makes it in our body. And it's still not going to be water soluble. So these extra carbons up here get cut off, and then another OH gets put on. Anyway, this one is estradiol. This one here looks really similar. Maybe to you it doesn't, but if you look, this piece here would make that missing ring. And so it will close up. This is what's found in soy. This is one of the 2 molecules that's found in soy. And I think this might be one of the other ones. Or oh shoot. I looked it up like 2 days ago and now I forget. This is found in some other plants. But they're called phytoestrogens. And I'm mentioning this because at some point you're going to pick a topic. You need to pick a topic that you go, I have always wanted to learn more about that. I have always wanted to learn more about soy. So your topic is not soy. You're going to actually pick the molecule. But whenever you see this prefix phyto, that means plant. And so these are plant estrogens. And so it was the myth that if you eat too much soy, you're going to get too much estrogen. And so then they were saying, well, women, when they're going through menopause, because your estrogen drops, like plummets. And so if you take the plant estrogens, it will help. One of the problems that's happened is we have put the soy products, we have so over processed soy that when you isolate individual molecules, they don't work the same as when they come packaged by Mother Nature, because Mother Nature packages them. We are not solid beings. We're actually, remember, 99.99999999999% of us is not material, not physical. We're actually vibrational beings. And so when we as humans think we can take the molecules out and it's going to work, you don't have the vibes anymore. So in places where people do eat the whole soy, they actually have much lower issues of the female cancers, of issues with menopause and stuff. And so it's actually it can be pretty interesting. So these are actually also ones that I call them guardians of our genome. They protect our DNA in certain ways. Anyway, those are just, there's so many. I could spend the whole time. In Chem 106, I spend more time looking at some of these. Those, again, I have a section like that in every one just to start whetting people's appetite. I could have dressed up like Leo. I might have him somewhere. No, I have his tail. All right, we're going to do alcohol reactions. And there's several. We're going to look at 3. And so normally I would do about an hour lecture and then we would go to lab and you guys could do this in lab. So last weekend I went in and made a video. And then I created a different lab because I was like, this is so silly. You're just like watching me do these reactions. There is going to be a lab where you're going to have to watch a video of me doing the reactions. So have no fear. So I wrote them really big. Dehydration means, we should do this one in blue, is that we're going to remove or lose water. So water is going to be a product. These guys always have a catalyst. And so in this case, it's H2SO4. So we'll start with 1-butanol, and just to make it easier for me, it's just how I draw it. You can draw it like that. That would be the 1. It would be better to draw it like that. And so it continues with the zigzag, but that's carbon 1. Either way is fine as long as you can see that corner. The reaction, nothing else is being added. It's just in the presence of this catalyst and heat. Sometimes I forget to put the heat there, like in your study set. So just add that word in there or on your worksheet. So to lose water, we could do cowgirl chemistry. God, I can't believe I totally forgot. I usually dress up with my cowgirl boots and everything. I have new ones from Brazil. They're sitting right over there. You wouldn't know it. Yeah, I'm dressed up as a cowgirl today. All right, so we're going to pull out the water. So there's the OH, and where it's going to get the H is on the carbon next door. So this is called cowgirl chemistry because you lasso the water. It can be cowboy chemistry too. It can be any cow chemistry that you want to lasso. It can be easier to see. The next one, I'll draw the carbons out, like on 2-butanol. If you draw the carbons out, sometimes it's easier to see. So we have the OH, and it's going to take the H from next door. The thing is on this next one, we're going to see it can lasso the OH in 2 different ways. It could lasso it this way, or it can lasso it this way. But how we're making the water is the OH is going to come off and the H from next door. That's important. So what we get for the first one, we still have our zigzags, but if we lose an H and we lose an OH, we have to make a bond there. And so we're going to end up with an alkene. You're always going to make an alkene. or a carbon-carbon double bond. That's the key to dehydration. All right. So again, for some students, you can do zigzags, realizing you're gonna go to an alkene. If it helps you to see it by drawing the carbons, you can do that. And you're gonna know it's a dehydration because it's gonna be in the presence of sulfuric acid and heat. And I meant to show that difference. So we have our 4 carbons. We could have either done the double bond here to here, or we can do the double bond that way. This is where often when I'm teaching it, still fascinates me. Doing it on paper, I think totally different than when I'm at the board. The star is where the OH was. And because the OH is gone, that bond has to go somewhere, and it can go either way. This, we get 2 answers. For a primary, you get 1 answer because it can only go one way. There's nowhere to go the other way. But on a secondary, we get 2 answers, and you can fill in your hydrogens. That would be left over. So you get 1 butanol, sorry, 1 butene and 2 butene. Now, I have to tell you, we saw before where we got more than 1 answer when we did like the saturated compounds. There is one more piece with this, that there is a preference. You still get both, but you label major and minor. Now, the good news is the rule is similar to before when we did alkenes. You only got 1 answer when we added to an alkene, and it liked going towards the center. It's a similar thing. It likes to go towards the center. That's going to be your major, but it can go the other way. So you get 2 answers now. All right. So you can do our butanol. There's our OH. There's our methyl. So if you do zigzags, that line just means a methyl. If you draw the carbon, the lines again mean hydrogens. There is another way to write heat. You can remember. And that is you show a triangle. So the triangle means heat. So you're going to see that happen in places as we go through the notes. So if you do it this way, you still have your zigzags. And what I like to do is I'll put a star. That's where my OH was. The carbons don't change. So we still have a methyl there. We don't have the OH. Where that OH was, you need to make another bond. So you can make the bond go to the left. You can make the bond, I'm going to make that go up. You can make it go to the right. You could also have made it go to the methyl, but that's the same as this one. So it can go left or right. The star is where my OH was. You end up with an alkene. Which one is major?
Is it the second one?
Yeah, it's the second one because it goes towards the center. They don't like to fall towards the outside, but they do. And I don't know what the percentage difference is. So that's the idea of dehydration. We'll see in 2 pages, you'll have practice with these and then your study set and stuff. And you guys have actually a huge advantage. So kind of for all of you is to realize your notes, you know, as you're taking them. It was something Kristen commented to me, that she kind of sits and listens as I'm going through it. She'll write a couple things down, but then she goes back and watches the video, because then she can stop it and take more careful notes, or going back and redoing your notes. Like me as a student, I always went back and rewrote my notes, because partially because your teacher, sometimes as I'm doing it, I'm trying to remember where I'm going here. But because these are going to be, since for your celebration, you get to use your notes. These have all the answers on it, or to then remake a note card or 1 page that has everything before the celebration. So you're not trying to go through everything and finding it. So just some suggestions. All right, the second type of reaction is oxidation, which is, we'll have to do, by the way, yeah. So next week is Sherpa New Year. It's like 1 week away. It's very exciting. It's going to be the year of the ox. We're only a week away if we make it. And it's even more exciting. It's a metal ox year on the Tibetan calendar, Tibetan Sherpa calendar. And so I thought that was pretty cool because it's like the chemistry ox. So it's the red ox year. Or if you like Leo Gur. So we'll put the ox. We need Leo. I've been busy making you guys a slideshow because your lab you're going to do has to do next week with, we were going to do it. We always do it in Chem 105. But so since half of you did not have me, what Leo stands for is losing electrons is oxidation. And I'm very sad we're not in class because somebody always for the celebrations likes to hold Leo because he's very cuddly. And somebody likes to hold the ox. And the one-legged ox is in the other, the three-legged ox. It's not a one-legged ox yet. It's in the other room. So when you lose electrons, it's called oxidation. There is, and GER stands for gaining electrons is reduction. So Dr. Russell taught me that. I love this because I have a Leo. My sister, I'm not a Leo. My sister is a Leo. And so she never took this. She's not sentimental. And so I took her stuffed animal. The original term for oxidation actually came from biochemistry. And oxidation actually meant to gain oxygen. And then they realized, I'm sorry, yes, that had other meanings. So this is before Leo Gur. And so in general chemistry, we look at it with metals and stuff. In organic chemistry, we look at the hydrogens. So when they lose electrons, it's also losing hydrogens. And so that's what our oxidation term is going to mean now, is we're going to be losing hydrogens. So GER is going to be gaining hydrogens. So it's kind of like a funky GER, because I don't know how you GER without an E, but you are losing electrons there. You're losing and gaining the bond. So when it gains a hydrogen, it would gain a bond to the hydrogen. So it's gaining electrons. So it's now like GEHR. It's like an extra and a LiHo. He would have to be LiHo. Right. Right. So we're losing hydrogens. That's why it says removing hydrogens, not water, which means we're not losing the oxygen. So 1-butanol, let's go back and draw it. You're not going to lose the oxygen this time. And so one of the things that happens with these reactions is we end up with a double bond because you're losing hydrogens. You're going from saturated to unsaturated, but you didn't lose the oxygen. The oxygen's still there, so the double bond's going to go to the oxygen. Where you lost the other hydrogen was, there was a hydrogen here and this hydrogen. These are the hydrogens you lose, meaning the hydrogen on the same carbon. You don't need to know that kind of detail. Really, all you need to know is dehydration, you go to a double bond between the carbons. In oxidation, you're going to end up with carbon to oxygen double bond. So in the one, you get a carbon-carbon double bond, and the other one, you get a carbon-oxygen double bond. Now, on the arrow, there are several different possibilities. There are many different oxidizing agents. So more for Melanie, because she's going into hazardous material stuff. These guys are all potent oxidizing agents. For our purposes, we will probably just say a bracket with O, and that just is a generic way of saying an oxidizing agent. You can pick almost any one. In the lab, if we did the lab, which I got to do, we use this guy, CrO3, because there's a color change that happens when something's oxidized. And so this has an orange color, and if it oxidizes, it changes to a green color. And I'll talk about that more when we get to a lab portion. All right. So there is another step. We're not going to go there until next week. I mentioned that only because some of you may look at, like, there's the book I posted for the class. Maybe none of you know there's a free textbook posted on Blackboard, or you might go and watch like Khan Academy. And there is another step. We're going to do it next week, and then we'll put it all together. But let's just right now get that it does one step. So 2-butanol, my OH is here. I'm going to oxidize it. The key with all of these reactions, the carbons do not change. And in this case, the oxygen's still there. We just make a double bond wherever the oxygen was. So that's oxidation. I was going to say something. I don't remember what it was. All right. T-butanol just means we make a T-butyl and we attach the OH to, this is the tertiary alcohol position. So what we have here is a primary, a secondary, and a tertiary. We're going to go back and name these. So we're going to try and oxidize it. And something very fascinating happens. So you go, okay, I'm going to take off that hydrogen and I'm going to double bond it. And hopefully somebody's going to say, well, that's wrong. What's wrong with my answer?
Too many bonds.
Yeah, there's too many bonds. It can't happen. Was that Ezra?
Yeah.
Okay. There's too many bonds. So tertiaries do not oxidize. So if you oxidize it like I just did, then please do your frowny face and put an X through it. It's a no reaction. NR is for no reaction. You don't have to, you can write no reaction or you can just write NR. So primaries and secondaries oxidize, tertiaries do not. All right, I have to do something about getting a better chair in here. I want to go through naming the products of the primary and secondary, because it is somewhere where we're going to be going next week on Wednesday, week from today. Is that crazy? I know a week ago today, you guys were all doing your celebration. I was sitting here twiddling my thumbs. This is an aldehyde and it's called butane. The AN is because the carbons have all single bonds. So that AN is really important. All the carbons are single bonds, and then we say AL. So I wanted to name it to point out something. When you write stuff, it's really important that I can read it, because we were doing alcohols and those have an OL. So I have to be able to see it definitely is an O, because if it's an A, it has a very different set of reactions. So this butanol, this is an aldehyde. And again, there is another step. The aldehyde keeps reacting, but I'm going to do that next week, partly because I ran out of room. Yeah. All right, that's an aldehyde. This one is called butanone. And this is a ketone. We're going to be doing ketones and aldehydes next Wednesday. So I'm just mentioning this so it's there in your notes. So when you do go to study for the celebration, you have the notes and it all does start keying in. And I'll talk about how we name them next week, but it does help to see a preview. So you're like, oh yeah, we did see those before. So what happens is a primary, you're going to end up making an aldehyde. A secondary is going to make a ketone. And a tertiary is an NR, no reaction. Does anybody see what's the difference between the aldehyde and the ketone? They're always taught together. They always share the same chapter in the book, but they're different. Anybody want to take a gander what the difference is? Well, one, what's the same is they both have a double bonded oxygen, but what do you think's different? It's okay if you get it wrong. Leo will still love you. An aldehyde is always at number 1. Always at number 1. That's why it comes from a primary. So the double bonded O is always on the end. A ketone, it's going to be somewhere in the middle. We just did a really short one. All right, one more reaction. There's my orange. Let's try purple. So Lucas reagent. You really have to get colored pens if you haven't. They're like so much fun. This one actually is really cool in the lab. All it does is becomes cloudy. It's not as dramatic as the oxidation. Tertiaries are the most reactive. They all do react. Tertiaries are the most reactive. They react like boom. As soon as you add it, the reaction has happened. In fact, all these reactions, that's something I was trying to show in the video. And yeah, so you'll eventually get to, in like 2 weeks, watch the video and see the observations of what's going on. So this turns, what happens with tert-butanol. Oh, this was the question. So there's our tert and the OH. You can show the OH above or below, but it's called tert because it looked like it was a tert-butyl and the OH is there. I do have a question. So somebody else, let's get their name on the board. What would be the IUPAC name of that? Maybe?
Would it be 2-methyl-2-butanol?
2-methyl what?
2-propanol.
Propanol. Was that Jeremy?
Yeah.
Okay. I didn't see you come in. There's like all these people here, and I don't know how you got in. It's like magic. I just think your teacher's losing it is probably what's going on. Yeah. So I mentioned that it drove students, it actually drove your teacher crazy in the lab. 2-methyl-2-propanol is the IUPAC name. So IUPAC is we always find the longest continuous carbon chain and we number. Tert-butanol or tert-butyl alcohol is a common name, and so most people, and so both names mean the same thing. All right, so what happens is we're going to add HCl, and the catalyst is going to be the zinc chloride. So catalyst is not involved in the reaction, and it's an exchange reaction. And so the exchange that happens is between the OH and the chlorine. So the OH is going to combine, these guys are going to switch places. And so we go back, same chain. Carbons all stay the same, and the chlorine gets put on there. Wherever the OH was, the chlorine gets put on. All alcohols will go through this. It's just the tertiaries are super fast. They happen immediately. It's actually a great way of classifying them because based on how the secondaries take a couple minutes, and then the primaries take like a couple hours. Eventually they all turn cloudy. And so this becomes cloudy, and that's how we can tell it. Our other product is going to be the H2O. So the OH and the H combine and we get H2O. So what happens visually is it becomes cloudy. what happens in the oxidation is you'll see a color change. And it's a really obvious and ugly color change. And it happens like as soon as it touches it. All right. So all of these answers are up above. So the ene to make the double bond between the carbons, we're going to start in every case here. We're going to, well, actually not in every case. With 1-butene, we're going to start with 1-butanol. And again, you can show the OH up or down. And the key is you have to show the right catalyst. So H2SO4 and heat. So this is a dehydration, just as a note. So a carbon double bond. All right, the one is the ketone. So that means we're making the double bonded O, but a ketone, it's in the middle. I'll talk more about ketones next week, so we'll just leave it at that. And so this is an oxidation reaction. So actually, these three down here are nice because they summarize the whole page we went through. So you can just show it as the bracket O. And in this case, the OH has to be at number 2. And the same with the last one, that the OH has to be at number 2 because I'm going to end up with the chlorine at number 2. And so that is called Lucas. I had a class 2 years ago. Just a really wonderful class, and they decided to call it, there was another reaction we did, and they decided to call it Leroy reaction, because they decided Leroy and Lucas were twins, and Leroy was neglected. And so brings back fond memories. You'd say plus HCl, and the zinc chloride would go on the arrow as the catalyst. So, opportunity for somebody else to get up on the board. How comes on the first one, I didn't start with 2-butanol like I did on the other ones? You could, and I would give you part credit. Go ahead, Caitlin.
Oh, I was just going to say, because it's in the first, it has to be at 1.
Well, what would happen if I started with 2-butanol? I can get there. I can get to the 1-butene starting with the 2-butanol. But the problem is you also get this too. So you get a mix of 2 different things. If you start with it at number 1, there's only 1 answer. If you start at number 2, there's 2 answers. And so that's what I was going for. So I would give you part credit because you had the right idea, but it would then be, you'd have to separate these, which becomes actually not so simple to do. So you're on the right track, but the full answer would be for that. All right. Again, these 3 down here, this was actually really nice. This just summarizes the whole page really nice and neatly. All right. I want to talk about the lab, and then we'll look at properties. So the lab is due next Wednesday. We are going to be talking about other oxygen families next week. And so you have to do 2 things with the lab. One, you have to pick from page 1. They're all 7-day challenges, so you can do any one you want. You do need to start by tomorrow, so if you haven't already started, ideally. So pick the one that calls to you. And then your second one, if you, you can pick something from this side, like making something spicy, making something with fermentation. And then with that, the class goes until about mid-March. If you want to do a 30-day challenge, if you like your 7-day challenge, you can keep going for 30 days. So if you start meditating, and again, if you're like Jeremy's done this with me before, that you can add another dimension. So let's say you already do some prayer, and so you can add another dimension, and it can be quite fun. The bean one is actually really tough, but it's a game changer. The other thing you can do for the 30 days, if you would like, you can say, yeah, I want to try the bean one, but to do it for 30 days, that's asking a lot. You can pick a different one each week for 30 days. So you can do one for the 7 days. That's going to be part of your lab. And then next week you can say, okay, I'm going to giggle and jiggle for 7 days. And then you say, okay, I'm going to meditate for 7 days. So you can pick and do a different one for 7 days for the month. With that, I also wanted to mention that some of you did a 30-day challenge for the first 30 days of the term. So if you did, there is a folder in this week that technically our class started on the 4th, but some people got a head start because they knew where we were going. So if you did, you can get that in this week. Or if you're like, I didn't start till the 10th, just you can submit it next week, that's fine. But for the next 30-day challenge, you got to pick either one of these that you're going to do for the full 30 days, or you can do a different one every 7 days. And the second half of the lab, so you have to do 2 activities. You pick something from this side. There's a couple art ones because some of you are really into art. There's the bread making. So some really cool bread that's in my next slideshow. All right. We're going to get into polyphenols next week. So I just wanted to mention that. So even though you don't have anything due this weekend, you probably want to do the one of the backside activities. If you're like, I really want to do 2 of the things on the front side, you can do that. But you do have to do at least one 7-day activity. You have to do 2 of the activities on the lab. And is there any questions with that? All right. So the labs, it says it's due next Wednesday. If something happens and you don't start till Friday or Saturday or something, that just kind of let me know. I just want you to embrace the lab and to grow from it. All right. And it does give you a little explanation with each. It has to do with where we're going next week. And right. All right. And also to give you a new territory for your 30-day challenge. So we're going to look at properties, and then I'll give you a break because the last 2 pages are practice. And so I'll give you like 15 minutes to play with it and we'll go through it. But let's walk through this page. So these properties change. 1, the boiling point. It is going to go up. These are going to have higher boiling points. And it is because they can H bond. So as soon as you see the OH, you got H bonding going on, that's going to increase the boiling point. All the ones we had before this, they were nonpolar. Also means our solubility changes. So what's going to happen? Actually, Kristen kind of already answered this a little bit, that they're going to be the small ones. If they have a small number of carbons, they will be water soluble. They will be hydrophilic. And as we saw on the first page, though, if they get too many carbons, so it's usually more than 6 carbons or 6 or more, it's a fine line. So yeah, I avoid, so something like this, decanol, that's too many carbons. So let's just say greater than, more than 6 carbons. They are hydrophobic. That's not like a firm rule because it has to do more with the surface area and how the 6 carbons are arranged, but that will work for our purposes, the idea of just looking at it. So I'm going to pause us. If you want, you can try these. You're going to pick the one that has a higher boiling point and then the one that's more water soluble. If you want to take a break, you can take a break. If you want to try some of the reactions on the next page, you can do that. So take like a 10 minutes, so quarter after. And all right, I'm gonna stop recording.